All right, let's see. So you said which final exam?
The
2022?
Yeah.
Okay.
No, it was 2023, my bad.
2023, this one?
Yeah.
Okay. And which question do you have in mind?
Start with number 1. That would be good.
Okay, right. So, first off, just so you know, right, we're not going to have tomorrow session 25 on the exam, right? So how do I put this? Yeah, that's all. This one, I mean, yeah, being able to use a table is a good idea, but we're going to cover superposition today.
Oh, that's what. Okay.
Yes.
Okay.
Okay, so that's why it probably looked a little bit foreign.
Gotcha, yeah.
Okay.
Yeah.
But okay, so this is how you approach at least the first. So it says use the above table to write an expression for the slope at the free end of a cantilever beam with a distributed load W naught across its length L using the convention described by your boss. Okay, so for this one, and I don't mind kind of going through how it's done. All right, oops, that's not what I wanted. I want this thing. That's really like almost a session. I'm going to put it in session 25 because it's actually a session 25-esque problem. So we're going to cover superposition today. All right, and let's just put this right here.
Maybe we could just do like the first part of that one and then maybe a different problem.
Sure. Well, whatever you like. Even the first part of this problem is something that's not, but I think it's still valuable insight in terms of, I think it's a good question. I'm biased. I wrote the question, all right? So I think it's a good question, all right? So let's talk about it since you wanted to know. All right, so the first question is, what is the slope? Oops. Oh, all kinds of stuff is going on here. The right end. Okay. And you're actually given this table right here. Okay. And this table tells us that we can figure out the deflection Wx using this formula. Okay. Now, let's just copy the formula over. This is the one that we kind of want. And, this might have been a little bit harsh and difficult, but we'll get through it.
Yeah, what I was confused about originally was I thought Wx was representing the distributed load. But then I realized it said in the question there were like different variables.
Right.
So then,
right.
Yeah.
Right. So this equation, so there are a couple of things here. To figure the slope at the right, okay, we actually need to take the derivative of this equation. Okay, so v of x is really equal to this w of x, all right? And the slope at any location is going to be equal to dv dx, okay? So it's a little bit tedious here because, and maybe I was a little bit cruel, but there's not really a better way to do it here, at least if you're going to use the table, okay? Because this is moment, this is shear force, and this is the displacement. Okay, and another thing to keep in mind is this displacement, okay, is going to be, it's going this way, so it's actually a positive downward, okay? So like, for example, if you plug in, if we come back over here, like if we plug in L, right, what do we get? We get 6L squared minus 4L squared plus L squared. Okay, so that's like 7L squared in this minus 4. That's like 3L squared. Okay, at the right end. Okay, so this has the opposite sign that we normally use because we know it's going downward. All right, so that's just another thing to keep in mind. Okay, so that this is actually v of x, the way we think of it, is actually equal to negative of this thing. Okay, now the theta, all right, this unfortunately, yeah, it's kind of tedious, right? But it's not too bad, but we can write it out as this. Okay, where we have the 2, and they're using q, all right? So we're, let's go ahead and we'll use w naught, okay? But this is not, this is only being applied halfway across, right? Whereas the table is giving us information across the whole span. Okay, so we can use q. It's fine. We'll just use q. Okay, so qx, and then this quantity. Oops. Okay, and then the other one, right? We're just using the dot product rule, okay, is going to be plus qx squared, and then this is going to be a 0, and then we have minus 4l, and this is going to be plus 2x. Okay, and as we said, this is actually all negative. Okay, so we put a negative in front. Now, what is this? This is an equation that describes the slope if you have a beam that is undergoing this distributed force across the whole thing. As we'll talk about today with superposition, this is not necessarily, well, we can use these relationships to describe different scenarios that are not the ones that we've represented by this equation, right? So this, just to be clear, right, this is now the slope as a function, you know, and this is for and if it's q, and then actually this we will define now using our convention v positive. Okay, is that clear? So how do we represent the system that we have appropriately? Well, this is interesting. At least I think it's interesting. We can think of this system and yes, that's not quite half, but you know I mean it's half. Okay, is equal to this. Okay, so this is not too revolutionary because that's the equation plus this. Okay, do you see this? All right. Okay, so now this left side is pretty straightforward. Okay, for calculating the slope. Okay, this one is still a little bit strange though. Okay, so how do we break this one down appropriately? Well, one thing to think about here is that this system can be thought of as having a distributed load across the entire thing, okay, and then I have some slope, okay, here. like that. Okay, and this is only L over 2. Okay. What happens over here? Well, it turns out that then this is just kind of along for the ride. This right half. And so it just stays with the same slope, okay, that we had already. Okay, so these then indicate that essentially what I need to do, right, I need to add the slope. So I'm interested in the slope here, which I know it's kind of going to go like this, okay, and it's going to be a negative slope, plus whatever the slope is on this one. So I could call this theta 1, and I could call this theta 2. And so that's kind of how we approach the problem. All right. Now, is this messy? Yeah, it's a little bit messy because I've got this huge equation. All right. So, and the other thing that's tempting to do, which is kind of a no-no, at least with this table, okay, it's tempting just to use the deflection at the end and try to take a derivative of it. But look, there's no x in this equation, right? This was solved for this. So in order to figure out what the slope is, we have to use the derivative of this expression that's still a function of x, right? This is just a value at the end. So what's that?
So you'd use the same equation that you just derived previously and then plug in L over 2?
Yeah, exactly. So
sign,
yeah, exactly. So for theta 1, right, now we can, let's go ahead and do some of the math, right? Here we go. So theta 1, okay, is going to be this one at the right of the long one. That one is going to be equal to this big mess. And in terms of the problem itself, let's use the W naught since I gave that. So we have 2Q, oh no, I just went right against what I said. W naught, and I'm at L, all right, so then I say L, and then we do 6L squared minus 4L squared plus L squared. Okay, so that's just going to be 3L squared. And then over here, I've got, well, I'll just write it out, plus W naught L squared, okay, and this is 4L, or minus 4L, so there's going to be a minus 2L here, like that, okay? So that's for theta 1. So theta 1 is going to end up being minus 1 over 24 EI, and we've got essentially a 6L squared, or 6L cubed, and I got that, so it's going to be 5. All right, so it's going to be 5. Did I do that math right? I'm not quite sure if I did it right. No, 6 minus 2 is 4, right? Is that right now? Do we agree? Okay. All right, I'm not looking at the solution, so I'm just doing it on the fly. All right, and so yeah, so this, anyway, we can, this is 1/6, minus 1/6. All right, now let's go to the other side. The other side is a little bit trickier, okay? I mean, I guess, fine, we can simplify this a little bit. We can say this is going to be minus W naught L cubed over 6EI. I think that's right. Okay, so then on the other one though, so what do we have? We have theta 2, and this one is going to be. Let me use a different color just so that it's not. Okay. So we have theta 2, is equal to minus 1 over 24 EI. And then we have what? Okay, so this gets a little bit trickier. This is going to be 2W0 times L over 2. I don't know, maybe I'll just, well, I know 2 times L over 2 is just L. So will you give that to me at least? So, and it's actually not minus. It's actually positive because it's the opposite direction. So this is going to be W0 L, okay, and then 6L squared. Can I do this? I don't know if I can do this math that well. Well, this is going to be minus 2, so that's minus 2. So then I've got 4L squared plus, now this is going to be essentially L over 4. Okay, so it's L squared over 4. So I've got 4 times 4, 6. Essentially, I got 17. Is this right? I think this is right. Okay. That's for this term right here. And then I've got a plus W0 L squared over 2, or L over 2 squared. So L squared over 4. And this is 2 times L over 2. That's 1, so it's going to be minus 3L. Like that. Okay? And we already said that the slope at this end is the same as the slope at this far end over here, because it's just going along for the ride. So essentially, yeah, the total slope is equal to theta 1 plus theta 2. All right? Yeah, so I don't expect, I said we wouldn't cover the principles we're going to cover today in the exam, but I'm glad you asked, because these tables allow you to do these types of interesting problems. And there are a lot of there are a lot of scenarios that have already been worked out that if you just search the internet, or you go to Hibbler's book, or you go to the notes, right, that you'll find the answers. Okay. Okay, did you have another question? Do you want to keep going on this, or did you have another?
No, yeah, we could move on. I didn't know it's the superposition.
Right, right. Well, it's good to know. It's good to know. All right, what's the other one? What's another question?
If we could do another deflection one, we could look at the second one on the homework. I was able to get it, but maybe we could go back and.
Okay, let's see. So 24. Okay, question 2. Let's see. Yes. Okay, actually, so were you here yesterday? We covered this a little bit, I think. Did we? I'm not sure if... Oh, maybe we didn't cover it yesterday. Okay, or we talked about it at the end. But let's go ahead and talk about it some more. Okay, so this problem is fairly tricky, okay, and kind of the first step is to make sure that we know what the internal bending moments look like, okay, and I think maybe we've done this before, I'm not sure, but the internal bending moments essentially look like, okay, so here we go. This is a beam. Which direction? Okay, this direction. Okay, and and pinned, rollered like this, and the bending moment it's going to have L over 2. It's going to have an interesting effect. This is an MAP essentially, right? And so an MAP ends up applying a if it's positive in terms of externally applied moment, it ends up for our convention being a negative, right? So we know that this is going to be this magnitude here is going to be MAP. Let's see, we'll just do it like this. Okay, well, I didn't quite do it like that. Okay, so this is MAP. Okay, and the actual line or lines, they're constant slope. Okay, there's no shear. There's no shear. There's no distributed load. Okay, which means that the integral of that is going to be a constant. So the shear force is just going to be a constant, and the integral of a constant is then a sloped line. Okay.
The way I did it, so I just did it with like the reaction or the reactant forces, and then with the external equilibrium. So on like the left hand,
Yeah.
had F1 going up.
Yep.
And then on the right, F2 going down to balance it out.
Yep. Yep.
And I was able to get the diagram based on that.
Okay, that's fine. That's fine. You can. I didn't ask you to use a differential integral method here for getting the diagram, but this is the diagram, right? And and so the line here, right? If we think about it, okay, the this. Well, let's do this, right? So for we have the following equation. It's going to be m of x equals the just the slope, which is going to be MAP, because this gives you, this is MAP over 2, so this needs to be MAP over 2L. No, over 2. No. It's going to be. Yeah, that's right. No, it's not. It's just MAP over L, right? Because if I plug in L over 2, then I get MAP over 2 times X, right? And for the L over 2 less than X, L, we're going to have, now there are a couple ways we could do this. Okay, we can describe, if we want, well, let's see, maybe we'll try doing it this way. I think this is a little bit different. We'll call this one X2, all right, and we'll call, that one will be we'll just call X2, and we can still use this as X, it only goes from there. So this is going to be M of X2, okay, and in this case it's going to be still MAP X2 over L, and then, but it's going to be minus MAP over 2. Does that make sense?
Your minus m out over 2 is just the y-intercept.
Yeah, it's just the y-intercept there. Okay. All right.
And also, this is assuming that x1 is coming from the left, x2 is coming from the right.
No, the way so in some of the notes and the way I did it before, I did say x2 is coming from the right. In this case, we're going to try doing it with x2 coming from the left at that midpoint and see how it works. Okay? So we'll just see. It could come out horribly. Okay, but I think we can get it to work this way. All right, and this is x over there. All right, so let's go ahead and write out our formula. Okay, which is that we have EI right is equal to this. Okay. So now we've got to do a couple of things. You know, we're going to do a couple integrals, and so it's also probably not a bad idea to just think a little bit about what the boundary conditions are that we're dealing with here. So first, right, we know that m of 0 is going to be equal to 0, right? And we know that m of x2 equal to L over 2 is also going to be equal to 0. Okay, so this is, we're doing it a little bit differently, right, by having this x2 going that direction. So that's this is a little bit of a weird thing, but that's how it's going to be. How it's going to play out. Okay. We also know, all right, if x2 was coming from the right, if it were coming from the right, then we have like this slope, you know, being like theta 1 here, and then we'd say it's equal to minus theta 2 coming from the other direction. Okay, the slope being the slope of the deflection, not the slope of the moment, right? There's a discontinuity there. Okay, so here what we can say is that, well, there are a couple things we can say. We can say that the v, this is lowercase v, right, at L over 2, okay, is going to be equal to the v at x2 equals 0. Okay.
Also, just one question.
Yep.
For the m of x2 equals L over 2, isn't that equal to 1/2 minus 1/2 the m applied? According to the graph.
So say that again.
For the m of x2 equals L over 2.
M of x2 equals L over 2?
Yeah.
No, I'm saying it's at the right.
Oh,
I'm saying it's at the right.
gotcha.
Okay? Yes, you're right. You're correct in that we can do this, like you're saying. And in fact, this information doesn't help us when we do these integrals, right? Because we got to integrate this, right? So we need two boundary conditions that are related to the deflection when we do these integrals. Okay? If we had started, say, with the shear force, then these boundary conditions would be helpful. All right. So anyway, so then the other one is that dv dx, where x equals L over 2, okay, is going to be equal to dv dx, okay, where x2 equals 0. Does it make sense? Okay, because we're going, this is the x, right? And we get to L over 2, and that slope has to be equal to, again, going from left to right, this slope. Okay? All right, so let's go ahead and let's do some integration. And again, this is a little bit different than I had done it previously, but maybe it'll be a little bit easier. Maybe it'll be harder. I don't know. So here we go. We have dv dx is equal to 1 over ei, okay? And it's going to be the integral of the moment. Okay, so we're going to have two equations that we're doing this for. We're going to have the left one and the right one. Okay, so let's, we can break this down and say that, okay, we have now 1 over ei, and if we use this upper one here, okay, this will now be MAP over 2L x squared plus a constant. So this is going to be okay. And then this one over here, okay, is going to be where we have yeah, this is right. And then we have a minus like that. Okay, we agree with this? So then now, what we can say here is that okay, so these, oh yeah, that's the other thing. Oh, I'm making it hard on myself. Okay, v of 0 is equal to 0, and v of x2 equal to L over 2 is equal to 0. Sorry. Okay, I'm doing this on the fly, so please forgive me. So, okay, so to see, because we need to figure out what C1 and C2 are here. All right, so now, and these are just attached, right, at these locations. So that makes this easier, right? So now we know that C1 is equal to 0. So we can write out that over here, this is just going to be 2E1. Okay, so that's true on that side. And then over here, this is a little more complicated, all right? So I can plug in that x2 equals L over 2 into these equations and set them equal to 0. So now I have, okay, so I'm going to go a little bit further. And say that we have this, okay, so L over 2, see that's when you going from the right would have been easier, okay, but it's okay. So we have L over 2, so that's going to be L squared over 4, okay, L squared over 4, that's going to be L squared over 8. So I have an M app L squared over 8, and I have nope, but there's an L that got knocked out, so it's just M app L like that, and this is going to be L over 4 plus C2 is equal to 0. Does that make sense? Okay, so then now I know that C2 has to be equal to that. I'm seeing blank squares. Did I do the math wrong?
No, and you used the boundary condition
Yes.
Dx2.
Yeah.
Okay, you replaced those conditions with the one you originally wrote.
Right, because these are easier. This is truth. These are truth, but then I had to set these equal to each other. And I'd rather not do that. Is that good? Yeah, so we're not really using, okay, or let's just put it this way. We've used these two conditions so far. Okay. Now, let's do another integral. So now we have v right, integral of this expression over here. Okay. Or I guess, well, yeah, we can just, that's fine. So we got to do these two. So we've got this mmap x squared over 2EIL. So this is going to be plus, we'll call it a C3. Okay. And this one down here, okay, so now we've got this longish expression. Okay. We're going to have, oh, I guess I should have, well, that's fine. I'll just, no, it's okay. This is correct stuff. Okay. But this one is going to be now a mmap x2 cubed, all right, over oh, I already put the last, can't keep track of everything. Here we go. This, and then this is going to be minus mmap over 4 x squared, or x2 squared, I should say. And this is going to be plus, so now we know that it's mmap, okay, so it's going to be this plus a C4. Does that make sense? Did I do that math right?
Oh, not sure, but yeah, the process makes sense.
Okay. 1/2, 1/3. Yeah, that all looks good to me. All right. So now what we have to do is we have to say that these two are equal. All right. Or now I'm going to use this expression. Oh, Aaron. How did... Aaron, no. Okay. No. This is what happens when you do things on the fly and you do them backwards and you do them in public.
Oh, use the wrong.
Yeah.
I was like, why is he freaking out?
That's why I'm freaking out. Okay. All right, let's just say that, and this is kind of fun. All right, you can see all the mistakes that one can do because I'm doing them. That's the relationship we want to use, all right? And so for that, what we have to do is substitute in, and so we're not going to get our C1 and our C2 out of this, okay? We're just going to get one more equation. So here, we're going to have that 1/2, and this is going to be plugging in L over 2. We got a squared over 8. So this is 0, okay, so this is just going to be equal to C2. Okay? Does that expression look right now? Yeah, so we're taking this equation right here. Right? We plug in 0 and we get C2 on the right side. And we're plugging L over 2 here and we get that. So that's the new equation. All right, so here, when we do this integration out, we get a C1x, right? And we get a we're going to say this is plus C3. And here we get, okay, we don't know this. Or we know that one, actually. We don't know this one. Okay. And this one is going to be a C4. Okay, just like that. Okay. All right. So now we can do, okay, we can plug in these relationships, okay, into these equations. All right, so we have, okay, so we're going to use these were used here, and these are going to be used here. Okay, so for this, we can say, all right, C3 is going to be equal to 0. Okay, we see that because we plug in, well, actually, no, we can't really, well, yeah, it is because it's times x, right? So this is C3 is equal to 0. Okay, so that's good. So that one's gone, all right? And then for this one, all right, we're going to have to solve and plug in all these things, okay, so that we get an equation for that still has C2 and C4 in it, okay? And then that's going to be equal to 0. Yeah, so that's kind of nasty, actually. Okay. All right, so then we've got these two equations right here, okay? But how many unknowns do we have? We still have 3 unknowns, right? We don't know C1, we don't know C2, and we don't know C4. And we have only 2 equations. So what do we need to do? Yeah, okay. And this is where we will, so, right, this is where I'm now saying we definitely should have used, well, I would have liked to have used it coming from the right. Okay, it would have made our algebra a little bit easier, but it's okay. We tried something adventurous. We tried something new. So here, Yeah, this is a little bit this is a little bit fraught. Um, Unfortunately, yeah. Because this expression doesn't really describe what's going on over here. This expression doesn't really describe what's going on over there. So like what we could try to do, for example, is to say, well, actually, we don't, how do you say it? No, it's fine. Essentially what we have to do, all right, is we have to use this expression right here. Okay. So now, what we can say, okay, is that at v of L over 2, so we plug in L over 2 here, all right, so we get mmap L over 2, so that's going to be 8, 6 times 8, 48, so we get L squared. And then plus C1 we know C3 is equal to 0, okay, is going to equal, now we have an opportunity to plug in this is 0, these all are 0 but this, equal to C4, okay. Did you see how I did that? So we're using this boundary condition, okay, that says that the displacement at the middle, right, where x is equal to L over 2 and x2 is equal to 0 is going to be the same. So that's the third boundary condition. So now we have 1, 2, 3 equations and 3 unknowns, and we can do the algebra. Okay, and that I'm going to skip. Okay, but if you look, all right, so these are the notes that, and actually, well, I can show you what I did at this point. Okay, so yeah, what I did is I did do x1 from the left and x2 from the right. Okay. Yeah, and so if you do that, I think it's a little bit more intuitive, but the boundary conditions that we're going to use are still still similar. Okay, where we're going to have the displacement being the same, right, the middle. The slope, though, is going to be equal to negative the slope coming from the other direction at the middle. And we know that the left and the right side are going to have 0 displacement, right? We have these right there. So those are still 3 sets of boundary conditions. Yeah. Actually, I accidentally did it wrong, I'll admit, a while ago. And then, because what I did is I said, oh, I'm going to assume that the slope here is 0 at L over 2, and that was actually a bad assumption. Okay, and then Michael was like, no, this is how you should do it, because he used these boundary conditions instead. Okay, but we saw how we could set it up a different way. All right, I wouldn't set it up that way. I would set it up going from the left and from the right.
Very good, thank you.
All right, other questions? Okay. Well, it's almost time to get started. Let's see here. How much battery? Yeah, we should be fine. Let's go ahead and close this. So today we're going to discuss session 25, Superposition, Indeterminacy, and Springs. First, though, I wanted to finish off session 24. And I guess the joke's on me. I didn't realize that we had about 45 minutes left in class.
Oh yeah, I was confused about
I
that.
was so well. Okay, so to my kind of credit, okay, if you look at the clock, it says it's 8 a.m. right now.
Oh.
Okay, and so I saw the hour hand hit the top, and or getting close to the top. I was like, oh my goodness, I'm out of time. But I had another hour with you all,
Yeah.
and no one told me.
I was gonna say something, but then I figured that, I don't know, we were just starting the office hours earlier. And
So anyway, I'm sorry. I honestly, it was while we were in the middle of office hours, right? You were here. Oh no, who was here? I think Kira was here, and Kavia was here. Anyway, I realized, oh my goodness, because I looked at the clock here, I was like, I had like another 45 minutes. So I'm sorry for that, but it's okay. We'll get through things today. So we'll call part 3 of session 24 kind of the way of the engineer in terms of how we go about solving for the deflection across a beam. And the idea essentially is that we take shortcuts, right? You're not going to solve the equations that we introduced yesterday, right? Where you have, for example, the second derivative of the displacement with respect to x equal to 1 over EI times the moment, okay? Or that's not the approach we're always going to take. So the approach is that you're going to look for these tables, okay? And Rourke's book is this old book that is kind of famous for having a bunch of these relationships worked out already, okay? Now, I don't think people say use Rourke's because there's the internet, so you can just search for tables, okay? Or you can look at Appendix C in Hibbler's book, all right? And so this is what one of the tables might look like. Okay? And notice a few things. I have like beware, beware, all right? I don't, there's probably, is that from the Wizard of Oz? Lions and tigers and bears. No. Oh my, that's not beware. There's some movie, some kids movie where they're like, okay, no. Okay, anyway, I don't know what it is. All right, so there's, just use a lot of caution here, all right? And so, you know, tomorrow I could say, all right, here's a table, and use this table to run a calculation, all right? That is possible, okay? But what does this table? This table doesn't use the same letters. It's very different. All right, let's take some notes. So first off, M stands for moment, so that's okay. In this case, the Q that they're referring to is actually what we call big V. Okay. All right, so that's the shear force diagram, and maybe that kind of makes sense, right? So they even put the moment diagram above the shear force diagram. Usually we put the shear force diagram on top. Whatever, okay? And then this W is what we call little v. Okay, that's what we call the little v. Now, notice, their positive v, all right, is downward, right? So like you see this W, L over 2, this is the max value, all right, at L over 2. So they're calling positive, and that's a little v, downward, all right? And so, and even these moments and these shear forces, they can be flipped from what we think, right? Because if I have, for example, you know, I know that in this case I have on the left side, I have P over 2 as my reaction force, right? And the way we define it I have a big V, right? Like this, like this, like this. Okay, so I know that at the left side, V of 0, this is a big V now, all right? That's the shear force. That is equal to P over 2, positive. But look, they use a different convention. They're saying it's negative, all right? It's below the axis. So this is also flipped. Okay, so this is, it's flipped to using a different convention than we've been using in the class. All right, and the moment, right? Remember what we said at the beginning yesterday? Positive moment is positive curvature. So we don't even have to do any of the math. This is negative moment, and we know this is going to have a positive curvature. Okay? So this is also flipped. So this would also be flipped. Okay? Any questions on that? So it's just to point out that when you find tables on the internet, be careful, all right? And, maybe I should be careful and not introduce this flippy-outiness right here. Nonetheless, I think we can keep track of things as we use some intuition, all right? The big one for these tables is that you want to make sure that you know which direction positive V is. And in Pibler's book, V is, or little v is positive, the little displacement is positive. The little v or the displacement is positive when it's up, not when it's down. But it's very common that you'll see in these other books that they define displacement as positive going down. Why? Well, gravity works downward, so often you've got a mass that's working under gravity sitting on top of a beam. Okay, so that's why you usually see the books writing the forces that are applied downward. Yes?
Is it just the graphs that are flipped because the equations are correct?
Yeah, so the graphs are flipped, yes. And here, yeah, this equation, you're right, looks correct here, right? So you even have to be careful with what we're using here, right? This is right, but this is not describing what's there, okay? And this is right, okay, but it's not what's described there. Okay, but, okay, let's see. If we plug in, yeah, in fact, this, so, and this doesn't match, like, if I plug in L here, right, I'm going to get a minus, oh, sorry, this is just L over 2. All right, so let's see. If I plug in L here, well, that's also 0, so that doesn't fly. You have to be, well, anyway, just be careful with these as well. Okay, good call, Andrew. All right, and here's another scenario that can play out where you have, say, a P that's offset some distance, okay, and we've got to be able to figure out the displacement, all right, at a location based on where the P is applied, so not right at the middle. So, for example, something that could be useful here, and maybe it's a little bit not so friendly, but imagine that, you are given a problem where someone says, oh, the displacement at this location at x equals L over 2 is equal to this. And you're like, okay, that's nice. And you're like, okay, it's a pin, and I know, okay, I can figure out then what P is, all right? And then if I know what P is, I could go back and I could plug in that P into an equation to figure out what the moment is. And if I know what the moment is, then I can figure out what the stress is, right? So you can use these equations or use these relationships of, okay, here's displacement at a given location to then figure out and back calculate out what the stress is based on the curvature or based on the displacement you might see. Does that make sense? Okay, so that's kind of working backward. So for example, if you were given, hey, I've measured the displacement at the end of this beam. This is a cantilever beam where a force being applied to it. I measure the displacement there, and I tell you it's made out of steel, right? And I go and I measure the cross section, and I got a BH cubed over 12. It's a rectangular cross section, so I've got I, right? So if I know the displacement, I know E, I, and P, or E, I, and L, right? I also know the length. Then I can figure out the P. I can plug in P into this equation, right? And then I can figure out what the moment is, right? That's maximum here at this location, and I can then figure out that sigma is equal to negative my over I. So you can do all this, making a few assumptions without having to even break out a force gauge. The other thing you could do is, if you have a beam hanging there, right, you could, apply a known force, look at the displacement, and then even figure out, maybe something like the I if you know the E. Okay, so but essentially you can play with all different types of combinations of these equations. Okay, and here's another table, right? This is for the distributed force across the entire thing. So just beware that some of these things don't work out completely here. All right, and so this is an example, right, where definitely, actually both of these examples, right, where they've defined the this is defined to be positive W down there, right? Which is, right, so if I plug in L, I get 2L, and then I get PL squared, right? So this is going to be a positive quantity at that right end, okay? And as you pointed out earlier here, that that this is negative, right? So this is, they say it's negative, but really it's positive across the entire thing, right? So these don't even line up with each other, right? This should really be on the other side, okay? At least according to this equation, or this equation should be negative, right? And this one has a negative curvature, right? We know that, and so M from our convention would be on the other side, and so this equation does match what's over here, but it does not match what our convention is. Okay? So just be very careful with these signs. Okay. Now, okay, so we've gone through some different tables. Any questions on these tables? What we'll do in a little bit is we'll show how these tables can help us use superposition to be able to calculate loads or results, deflections from scenarios that we don't have in a particular table. Okay, but that aspect will not be on the exam tomorrow. The other kind of quote way of the engineer is to use finite element analysis. So here's we're going to do an example, okay, that uses FreeCAD built on and uses calculus inside of it to do finite element. All right, and here's the example of the scenario that we're going to simulate. So we're going to say as a length of 1 meter, it's just a cantilever beam first off with a force applied at the end, and we have the beam has a width of 0.2 meters, and then it has a thickness of 0.1 meter, and we're going to apply 1,000 newtons, and we're going to use aluminum. Oh yeah, that's right. Yesterday you guys decided you wanted to make a deal with me, all right? The first question, well, okay, there will be a question that asks, what is the elastic modulus of steel? Right, because you guys looked at the previous exams and we said, okay, what is the elastic modulus of this? What is it? So anyway, the elastic modulus of steel is around 200 or 210 gigapascals, right? So That's something you should know. All right, so let's go here. And we're going to use FreeCAD to do this. So this problem, we don't even use pre-POMAX. Oops. Okay. Let's see here. We're going to create new. And then once it's up, we're going to go to part, not part design, like this. And then we're going to hit the cube right over there, and we're going to change its dimensions. So we're going to use a length of 1,000 millimeters, a width of 0.2 meters or 200 millimeters, and a height of 100 millimeters, okay, or 0.1 meter, like this. Like this. Okay, whoops. Okay. All right, and so you've seen us do this before when we did pre-POMAX. Now, and you can do beam bending in pre-POMAX. This is just to show another way of doing the problem using FreeCAD. And it's not necessarily, I mean, I guess it gives us a lot of the same information, but it's pre-POMAX is a little richer in terms of doing the finite element. So people call finite element analysis by the name finite element method as well. So we're going to do FEM, and that will bring up some new little icons here. So we're going to do, first you click on analysis container, all right, and then that brings up this analysis tab, and we're going to then go ahead and pick out a material. So I clicked on that little sphere that's now no longer a sphere. I don't know why that sphere represents material, but that's how they have it set up here. And let's use, I think we said we're going to use aluminum. So we're going to use aluminum generic, and that's going to have a elastic modulus of 70 gigapascals and a Poisson ratio here of 0.35. Okay, and then we got to add. So we're going to add the entire thing. So we're going to do add solid. Whoops, there it goes. Okay, like that. So now it's there, and we hit OK. So now we're in analysis mode, and you can see the material solid. That's great. All right, so we kind of move from left to right here. Let's go ahead and we're going to set boundary condition for the left side being a constrained surface like this. So this one we're going to do add, then hit that surface, and that's now constrained. Okay? It's a fixed constraint. That's essentially the wall constraint. And then we're going to come over here, and if we look back at the diagram, okay, I'm going to close this right now because I feel like I'm probably putting a lot of strain on my computer. Haha, strain, stress. Okay, so we have a force P that's being exerted over here, and it's going to be 1,000 newtons. So we come over here, and we click on this icon, which represents constraint force. We're gonna, let's see, I'll click on it like that. I probably have to add, yep, add first, then click on that. And that's coming out. That's not what we want. So we're gonna change the direction by first clicking there, yeah, or okay, I thought we were gonna first hit there. And then I'm gonna click this little edge, which will give us the option, okay, to have it normal. Okay, like that. But gravity typically acts downward, so we're going to go ahead and we're going to flip it. So we're going to reverse direction over here, like that. So now it's acting downward. We hit OK. We need to add a mesh, and in order to do that, we actually come over here and we click back on the geometry, and now we can add a mesh. This is not necessarily the most intuitive. I've done this before, but we're going to do max size for a mesh of 20. And we're going to do fine, and then we'll hit apply, and okay. All right, so now we've got our mesh. That's not the greatest mesh in the world, but it's fine for now. And then you click on this icon, which is solver. All right, which might be, let me see, maybe I should, so you can see later if you want to watch it later. Okay, down here, I clicked on solver. Okay, and that brings up this solver over here. And then down over here, you click on these three, or these two little extension arrows. Okay, and it's not letting us solve because I had to click, okay, now I click on the solver here, okay. Now this is selected, and then I come over here, and then now I can run the solver calculations. So I click that, and then we wait. And it probably will take, I don't know, 10 more seconds. 1, 2, 3, 4, 5, 6, 7. All right, looks like it might be done. Okay. And, oh, no, now it's done. So it's closer to 10. All right, and now you see the CCX, the Calculix results. And if I double click on that, then I get this interesting tab here. Okay, so what are a couple of things that might be of interest to us? Well, right now we're talking about displacements. So let's see what we calculate for displacement. So if we had used the table here, all right, we could figure out that the displacement should be that force, that 1,000 newtons times 1 meter cubed over 3 times 70 gigapascals. And I don't know what I is, but I think I calculated it out. That would have been here, okay, the BH cubed over 12, so it was 0.2 meters wide, 0.1 meter tall, and then so it's cubed over 12. So this is the I. And if we, hello Dylan, and then if we plug these values in, okay, we get a displacement of 290 microns. 290 microns is equal to 0.29 meters. So it's probably too hard to see here, but Z is actually upward. So if we look at the displacement, what do we get? We get minus 283, minus 283 Newton meters, okay? That is going to be, oh no, that's not right, sorry. No. Wait, the maximum. Did I put a wrong, did I not put the right in? So the minimum, the displacement, in the Z direction, is this not right? Well, let's see, the displacement magnitude, oh, 280, yeah, that's right. This 285 Newton meters, but I calculated out 286 microns. Okay, so wait, did I do something wrong with the dimensions? Hold on, let's go back. So we're going to close this. Did I put something wrong? It's off by, oh yeah, the force is 1 Newton instead of 1,000. So that's the reason. Okay, so that's why it's off by a factor of 1,000. Okay, so let's come back here. We're going to put in 1,000. Okay, make sure it changed it. Yes, it changed it. All right, that was scary. We're going to go to solver and we're going to solve it again. Okay. So one of the things, if when you take multi-physics, all right, which is our course on simulations, which involves a significant amount of finite element analysis, in addition to finite difference, in addition to some particle dynamics. One of the things that I emphasize is making sure that you do the simple simulation first, okay, and comparing it to an analytical model if you have. Right, so that was the case where I didn't compare, or as I compared it to my analytical model, I realized that something was not right. Okay, so maybe I had put in a material property incorrectly, maybe I had put in a force incorrectly into the system. Okay, so now, here we go. Now see, if we look at the displacement, it says minus 0.28 millimeters. Okay, and that is close to the minus 0.29 millimeters that I got there. Okay, any questions on that? Now, ideally, I've calculated out also a stress, a bending stress. Where is this bending stress? Or where would you calculate the bending stress on this beam if you're concerned about failure? Yes?
With the top or the bottom?
Yeah, the top or the bottom, and more specifically, Andrew, where more specifically? Top or bottom? Okay, well, yeah?
Where the moment is the greatest.
Yeah, okay, where the moment is the greatest, and where's the moment the greatest? At the wall. That's right, okay? So that's where you would calculate the bending stress, if you're concerned, right? And so that's what I did. This is saying there's an internal bending moment up here, okay? And it's going to be a minus PL, actually, right? And that makes sense because this, now we know the curvature, right, dictates what the internal bending moment, the sign of the internal bending moment, okay? So it is negative. The thickness, this will get me and maybe get you as well, is h over 2, right? Or the thickness is h, but the y that I could be concerned about is half of that, okay? And then I have the I, and this ends up being, I think it's 2.9, if I'm not mistaken. I have a point there, 2.99 megapascals. Okay, so let's take a look. What do you think it's going to tell us? And should we trust it? So let's, now look, we even know things about principal stresses, right? So which options would you pick here if you want to get this bending stress? Or which option, or options? There are a couple that should give us a pretty good idea. Or maybe a few that will give us a pretty good idea. What do you think, Dylan? Which one would you pick?
Let's say no principal stress. I can't really read that.
Oh, it says, okay. This one says von Mises. This one says max principal. This one says minimum principal, and this one says max shear stress.
So I'll pick max principal stress.
That's a good shot. Okay, so if we do max principal stress, okay, what do we see? Well, we see that, actually this is interesting, it didn't do the coloring. Usually it does the coloring. Let's see. No, I don't want to do that. Nope, no, that's not what I want. I think it's because I went back. So let's see if we go back. Yeah, there we go. Whoops. Okay, here we go. No, that's not good. Active task. Okay, yeah. All right, well, I'm a little bummed that it's not showing it right now because it's supposed to be. And I'm not quite sure what happened. But anyway, The max that it calculates is 4.6 megapascals. So now we ask ourselves the question, why is that a little bit off? Well, the reason it's off, okay, is, well, there could be other things happening, quite frankly, but one of the things, it could be, well, yes, what are the other things that are happening? That's the question. That side is constrained, completely constrained, right? So just as we talked about before, we have a Poisson effect of happening in this material, but we've constrained that side completely. So that means that the material cannot shrink in the vertical and it can't shrink in the lateral directions, in the width direction of the beam. So the maximum principal stress could be affected by that. Another good guess would be the von Mises. Okay, the von Mises, all right, is supposed to be telling us what the equivalent stress would be, right, to a tensile force. Okay, and that one comes out to be 3.2 megapascals. So that one ends up being a little bit closer. Okay, another option would be the minimum principal stress. The minimum principal stress, right, that would be on the bottom side. That's going to be the most negative. Okay, the most negative one is the flip of what's on the top. Okay, so that one comes out to be like minus 5.2 megapascals. All right. The maximum shear stress would be about half, right? Because why is that? You're like, well, wait, but there's transverse shear. Well, remember, this for a beam that's somewhat long, we don't care about transverse shear stress, right? We haven't really said, we know how to calculate it, that's very nice, but the transverse shear stress is typically very small, okay? So what happens? Well, we have in a beam, for a long beam like this, what dominates is the bending stress. The bending stress dominates. So the bending stress is just almost essentially like uniaxial loading, except it varies as a function of where you are above the longitudinal axis. Okay? So if I have uniaxial loading, right, what is the equivalent maximum shear stress? Well, we use Moore's circle, right? Moore's circle says that you've got sigma 1 equals something, and sigma 2 and sigma 3 are equal to 0. So that means it's just the radius of Moore's circle, and the radius is sigma 1 divided by 2. Okay, so once again, we see that when we do this, right, this is going to be 1.7 megapascals, and if you double that, right, that's about 3.4 megapascals. Any questions on this? Okay, so any questions or thoughts? Just because there's a computer and a finite element package doesn't mean that you should trust it without doing some of the back of the envelope calculations. And that's what's one of the powerful things about what we've talked about in this class, and as we're wrapping it up. All right, so I'm going to go ahead and close this. For your assignment, okay, you get to have the opportunity to run one of those simulations. And I wouldn't do the assignment, I wouldn't do that problem tonight unless you're all set and ready to go for the exam tomorrow. Okay, this is due Friday by midnight, as are 2 other problems that we're going to have. Okay. So let's move to session 25. So none of this is technically going to be on the exam tomorrow, but it does help us, and you might think, oh, maybe I can use some of these techniques, all right, to solve the problems. If it explicitly says please use the integral method, all right, to calculate out displacement, please do not ignore that suggestion. But you can check. People ask, can I put the tables on my note sheet for the exam? Yeah, sure, go ahead. That's fine with me. You can put you can put answers from the tables. That doesn't matter. We still, again, if we say use the integral method and there's no work there, and you just have the answer, right? That's not following the direction exactly. But I think having a few of the tables or a few of the values from the tables on your notes is a great way to make sure, great way to check what you're doing. Okay. Oh, that was from the office hour business. Today, we're going to finally finish beams, at least for this class. Beam 6. We've spent 6 sessions talking about beams, right? I don't know how many times we've talked about bars. I don't know how many times we talked about shafts. But here, at least, I've labeled 6 times that we've talked about beams. We're going to use superposition to calculate deflections, as you see in these kind of illustrative graphics. We're going to discuss indeterminacy yet again, but in this case, it'll be for beams, and we can then be grateful that we don't have indeterminacy on the exam tomorrow, at least with respect to beams. Okay? You and I are both grateful, trust me. These tend to have a little bit more algebra and are a little bit more difficult to figure out. And the final thing is just showing how beams can be springs. So we talked yesterday kind of potentially ad nauseum a little bit about how springs or how beams with some stiffness, right, will have a resonance that's based on their stiffness and their mass. And then we talked about the washing machine, which is a little bit off topic. I don't think many cantilever beams are used in the washing machine springs. Okay. We've talked about superposition in the past, and we can think of going back now to the bars where you have one force and then you add another force in the same direction, or if it's in the opposite direction, then subtracting from it, but that net force is going to contribute to having displacement. And so if I have 2 forces of the same magnitude, then I'm going to have double displacement. With beams, it's even more interesting in that we can begin to think of superposition with displacements, not just in terms of, okay, this is an increased axial load, but also I could have loads being applied at different locations and be able to still sum up the displacement. Okay, so, for example, here's a beam that has 2 loads with at two different locations. Right? The loads are P and Q. This is cantilevered, and it has some dimensions that are given to us. We won't go through the we won't go through the integral equations to solve this problem. Okay, that could be an approach that you take. All right. For example, you figure out what the moment is across this beam, and or you figure out what the moment is across this beam due to P1, and you figure out what the moment across the beam is due to Q is, and then you sum those displacement curves up against each other. Okay, that's one. We won't do that, but what we will do is we'll think about just drawing diagrams and using tables to solve this problem. All right, so if I have just that force P applied, then I have a displacement on the right side that's due to that displacement, to do that force. If we have a force Q applied on the right side, then I can think of a displacement, again, at the same location at the end due to that Q. And so what we see here, just by kind of drawing these out, that the overall displacement is going to be equal to the displacement due to force P plus the displacement due to force Q. Okay? That's superposition. Pretty straightforward, right? It's like, I don't know how to describe it. You have a bridge and you have one car on the bridge at one location, right? And you have another bus or another car and maybe a bus at two other locations. I can take all the vehicles off the bridge, right? And I have theoretically zero displacement, but then I add one of them, and then I add another one, then I add another one, right? But if I have them all there at the same time, the overall displacement at a specified location is going to be based on the superposition of these three vehicles. So now that makes sense. How do we use the tables that we just talked about in the last session? Right? Well, here is a set of tables that are potentially, of course, beware, they might have different sign conventions or things will be incorrect with them. But which of these equations do you think are going to be the most useful if I'm interested in figuring out the delta P and the delta Q? Yeah?
Yeah, the last one, the W.
Yeah, so that WC, right? Or that WX, right? Definitely, right? If we go back here, this one looks a whole lot like this one. Okay? Right? So, like, check, that's good, right? This loading situation looks a lot like that. This loading situation looks a little bit different, though, right? Because like the displacement and the force are not at the same location. So what do we do about that? What do you think? How do we how do we hack that out? Well, what we could do is the following. We can write that same set of diagrams that we had previously, but we're going to go a little bit further. Okay. Hold on. Okay, so this is all. Okay, so this is another important thing. All right. To keep in mind. I want the order to be different. Okay, this is what I'm trying to get at, okay? Do you see that there's no shear force and no bending moment in this portion of the beam? Right here, right? If I take a slice here, there's nothing going on. No internal force, no internal shear force, no internal bending moment. Okay? So what does that mean? That means, once again, that this portion, okay, I'm not talking about this right now, I'm talking about this. This portion of this beam is along for the ride. Okay. What do we mean by along for the ride? Well, we've had this happen before, right? When we did uniaxial loading, we had a force applied at some portion of a bar, right? And then the rest of the bar was just along for the ride. And it's a little bit more complicated here. It's along for the ride, okay? But it sloped at the end. You see this is sloped. Okay, so I have a force here, or imagine it's this scenario, right? That bends down, right, like this, parabolically, quadratically, better said, I guess. Yeah, like, so it's going to be, it's like, sorry, not even quadratically, it's an x cubed and you have an x, but yeah, to the third, okay, that bends down, and then there's a slope coming off, and the beam, right, the displacement at this location is not the same as the displacement at this location. Does that make sense? Right, because that thing is at an angle. This like goes back to like the very early problem that we did where we had a set of bars in a network with each other, and we said, hey, here's a situation where you have rotation, here's a situation where we don't have rotation. Remember? And when there was rotation, there was an additional displacement because of the length of the non-deflecting cross sections. Okay, so this one, there's no additional deformation, okay, from this point to this point, meaning the beam is just hanging out, all right, but it's not experiencing a further deformation. It's just along for the ride, but it has a slope associated with it. So that means that what we need to do is we need to figure out what the slope is here, so that we can figure out how much further down it's extended on that side. Okay. So if I know the angle here, right, and I know how long it is, which I do, it's L over 2, then I know that I can think of as a hypotenuse. I can figure out how much further this delta P is from, let's call this delta 1, where P is. Okay, so how do you figure out the slope? Well, the way to figure out the slope is from a table like that we have here, where they don't give us the slope, is to take the derivative of v with respect to x. Remember that theta is equal to dv dx. Okay? And what is v? V is given here. That's the w, right? So this is the v, like that. Okay? And remember that in this case, v going down, little v going down, this is positive, right? This is displacement. Okay? So theta is going to be equal to dv, little dv, or little v dx. Any questions on that? Okay. So that's what we have here. This v of x is just copied from here. Okay? And this can be used in this expression to figure out what theta is. Notice I cannot just use the displacement at the right end to figure out what the slope is. Why? Because there's no x. It's independent of x. That's just like a number. Okay? You have to use the expression that's a function of x to figure out what dv dx is. So that's kind of a bummer, right? But that's given here. So we take the derivative of this, and we get this expression. Okay? And then once I know this theta, we can calculate out what that additional displacement is, plus delta 1, right? Because delta 1 is going down. What is the equation that we use for delta 1? Well, we could just use this one if we want, right? Except what do? We substitute in L over 2 instead of L to the equation. Does that make sense? Because that's essentially, so what we're saying is it's a cantilevered beam, like I'm just chopping this off, all right? And that's a cantilever beam, just like this is, but this has length L over 2 instead of length L. Okay. All right, and just to make this thing not confusing for anyone, I'm just going to erase that. But you get the point. That is, does anyone have a question about this? Is this pretty clear? Okay. That, now, which is going to have more displacement? At least when I say which, I mean, do you think delta 1, assuming P and Q were the same, all right, I had to make that assumption, I guess. If P and Q were the same, would delta 1 over here or delta Q over here have more displacement? What do you think, Josh?
Delta Q.
Yeah, delta Q has more displacement. Why?
The length is, the only difference is the length. Which is
Yeah.
longer, so.
That's right? So if I use that like bottommost equation right here, right, and I plug in L over 2, right, I'm going to see that, yeah, of course, it's going to be bigger when I plug in a complete L. Okay, good. So now I figured out the slope, and I know I can figure out the displacement, okay? And so delta 1 is equal to that, and theta 1 is equal to that, all right? And so now I can use this, this idea, okay, that this is a hypotenuse. If I take the sine of that, I can figure out what the sine of this angle, sorry, then I can figure out what the vertical displacement is, okay, and that's what delta P is. Delta Q, all right, is just the equation that we have right here, okay, and so we sum these up with each other, okay, and we get this expression. Is this easier than using the integral, like doing the integrals? Yeah, I'd argue yes, right? Because you have some complex, somewhat complex functions that you have to integrate over. Okay. So this is where the tables can be useful for us. All right. Yeah. So that's that. Okay. Here's another example, okay, where we have a P and a Q across a beam that's simply supported, okay, and we can use another table, okay, and we got to be careful. And in this case, all right, this table tells us what the deflection is when you have a P that's not centered. Okay, so and it tells us that that B, all right, is a different value, okay, over this length, all right. So we have kind of these two terms, all right, where we have an A and we have a B. So if you know that, for example, A is equal to L over 2, right? That's this scenario right here. Okay, but you could have A equals 0.2 L. Okay, that's where B is being applied. Okay, and so then you can use this expression right here. Okay, and in this case, it's more straightforward because the table, the equations in the table describe what happens when you have the force applied in one location and the displacement measured at another location. So you can just use the tables here to help us figure out what the delta 1 is and what the delta 2 is without going through the same kind of thought process that we had where we had to like think about the slope. So here all we use are the delta equations. Okay, and this delta 1, all right, comes from this second equation right here, okay? Because we're saying that x is greater than a. So a was equal to L over 4 in this case. And then x is the location of the displacement that we want, and that's going to be happening at L over 2. Okay? And b is the distance from the P to the end of this right here. Okay, so b is equal to 3L over 4. Then for delta 2, okay, we just, well, anyway, you can do it a couple of different ways, okay, but this scenario, all right, is going to be either from a previous table or from when you have a is equal to x, a is equal to L over 2, and you just plug it in, all right? And then you sum these together, and this is the overall displacement. Okay. Any questions on this? So again, this saves you from having to do the integrals, okay, just by using the tables. Okay, so that's that. That's that. I don't know if people want to write anything, but that's this. And again, this is not going to be on the exam, but this should be something that, if someone asks, did you cover superposition with beams? Yes, I did. Okay. All right. Indeterminacy. Well, we've done this a few times now. Anyone want to shout out? What does it mean if you have an indeterminate system? Yes, Dylan.
More unknowns than equations.
That's right. Okay, so when you do equilibrium, when you perform the balance of forces and moments, you're going to get a situation where the number of unknowns is greater than the number of equations that you have. And so our typical process, right, is to think about having to use geometry and constitutive relationships to be able to solve the problem. An indeterminate system, the number of reactions is greater than the number of equilibrium equations. And the degree, now we'll even say that there's a degree of indeterminacy that's determined by the number of reactions we can remove to get a determinate system. Okay, so what does that mean? Let's think about this for a sec. This system is determinate. Okay. What is another way? Okay, so I can do the equations, let's do the equations out, right? If we do the equations out, we'll see that we have 3 reactions and we have 3 equations, all right? And this is just for doing external equilibrium, okay? Just for external. We haven't gotten into the internals yet. But once you have all the, once we know these external forces, we can do the internal moment and shear force without too much difficulty. Okay, that is one way of looking at it, all right? An indeterminate system, if we do all the math out, okay, what we'll see here is that we have 3 reactions. These are external forces plus a moment, and 2 equations. So this is indeterminate. We can't solve this without some additional information. Another way to look at these problems, okay, and this would be, yeah, indeterminate to the first degree because we have 1 extra unknown. Another way of this, to look at this problem, is ask ourselves a question: how could we convert this system to a determinate system, okay, for the degrees of indeterminacy? So let's go back when we ask. So let's ask ourselves the question, going back here, all right? How could we convert it to a determinate system? Well, blast, it's already a determinate system, so that we don't have to do anything. But when we're trying to convert this to a determinate system, what we're thinking about is removing a constraint. Okay, it's over constrained. All right, and so, for example, if it's a determinate system, you can't remove any constraints. What would happen if I removed the roller or the pin in this system? Yes.
It wouldn't be static anymore.
It wouldn't be static. It would just start spinning around the remaining constraint. Okay? Assuming that that P stays normal to the surface, anyway, you know, it'd even be accelerating if there's no damping, right? If now, okay, we go back to this example. Okay, or let's go back here. How do we make this determinate? How do we convert it to a determinate system? What do you think, Vivian? How do you convert it to a determinate system? Or maybe I should ask, what could we take away and have it be a determinate system? That's maybe a better way to say it. Or what constraint could we take away? And then it would not be the same system, but it would be determinate. Like, it wouldn't have the same displacements, it wouldn't have the same bending moments, but it would at least be something that we could consider to be determinate. Any thoughts? Okay, Dylan?
You take away the roller.
Yeah, if you take away the roller, right, then it becomes just a cantilever beam with a force on it. And we can figure out what the bending moments, or we can figure out the relationships between the moment, the reaction moment, and the reaction force on the left side would be with that P, right? So it's not the same system. Maybe I should, it's been changed, but this has degree of indeterminacy of 1 because I only need to take away one constraint. So the number of constraints that you take away that then make your system determinate is the degree of indeterminacy. Okay. So let's do some more examples. The one on the left, all right? So how many constraints do you take away to make this one determinate? How many constraints? The one on the left. We're going to do the ones on the right in a second, but the one on the left. What do you think, Shane?
On the walls.
Yeah, take away one of the walls. All right. So one of the walls. How many constraints are in a wall?
2.
Right. So this has the degree of indeterminacy of 2. Okay, because a wall is going to have a constraint on the force and a constraint on the moment. Okay, so this has 2 degrees of indeterminacy. Okay. What about the middle one? Alexis, you want to give it a shot? How many of those rollers would you take away and have this be? Yeah, that's right. Okay, so you can still have P, Q, and R there, right? But if you take away 3 rollers, that would then get us to a determinate system. So that's the degree of indeterminacy of 3. Okay, and then the one on the right. Anyone want to guess? How many rollers do you get to take away there? I guess Marissa, you're the only one I haven't called on. Okay. So how many rollers could you take away and still have this system be determinate? Or make this system determinate? Okay, so if you take away 3, 1, 2, 3. Now I've only got a pin and I've got forces on it. So what's going to happen here? This thing's just going to swing by a pin, right? So that's not a determinate system. That's not a static system. So how many would you take away then? Just 2, right? Yeah, just 2 because now I've got this and this, and I can support all those forces with it still being a static system. So this is kind of the easy way, without doing any math, to visualize the degree of indeterminacy for a given system. Okay. So that's one thing, right? We can figure out the degree of indeterminacy. How do we solve these though for their displacements? You have an indeterminate system, and if we're going to use the integral method, we just keep on plugging. Okay, that's pretty much it. If we're going to use the integral method, okay. So we have boundary conditions, we have continuity conditions, and we work it. Okay. So here, this is, well, obviously this is an indeterminate system. It's indeterminate with degree 1. Okay. And we can do our first step, which is external equilibrium, and then we've got some equations, but we don't know exactly. We have relationships between RA and RB, and we have relationships between RB and ML, right? But we have three unknowns with 2 equations. Okay, so then we're going to go ahead and start to break things down and do some slicing. Okay, so we've got the ability to calculate some moments, but again, this is messiness because we don't know what RB is. We just have equations. Okay, and then here we write out, okay, this is what the moment and will be relative to the second derivative of displacement. Still don't quite know, right, what RB is. And this is now an integration of that equation. So this would give us the slope, all right? And now, all right, do we have a constraint on the slope anywhere? Yes.
Yeah, at A, it would be 0.
Right, so at A, that slope is going to be equal to 0, right? So that might help us out a little bit, okay? Also, once we do this integration, right, now we have an equation for displacement. Is displacement 0 anywhere? Yeah, it's 0 at A as well, right? So now we're starting to see, oh, okay, I can plug in some values, all right, such that I'm going to have some interesting behavior, right? Or I could choose different ones, right? So, for example, I know that the displacement here at B is also equal to 0. So that might be easier, right, than saying that the displacement A is equal to 0. Why? Just because we defined x coming from the right. Okay? So let's do this. We'll say at x equals 0, the displacement is equal to 0. That means that C2 is equal to 0. So that's nice. At x equals L, we said that this slope is going to be equal to 0, right? So coming out of a wall, the slope is always 0. And so now we can plug in L to this equation, or sorry, to this equation right here, and that we can solve for C1. Okay. So now we've got we've got the, well, actually we can solve. We have C1, but it's in terms of RB. So what do? We now look at x equal L, and that will be equal to 0. Okay. And now we have 2 equations, this equation and this equation, all right? where we have two unknowns. We have RB and we have C1. So now we can solve for RB and C1. So here's C1 coming out, and here's RB coming out right here. Okay. So now we have RB. Finally, we did all that work so we could get RB. Now if we have RB, we know RA. Okay. If we have RB, we also have ML. Okay. So now we can figure out the end result. Okay. Any questions on that? You say, oh, did you really use constitutive relationships? Yes, we did, right? Constitutive is relating the internal forces to displacements. Where are the constitutive relationships in here? Right here. Right? Well, that was the second derivative of the displacement is equal to 1 over EI times the moment. Okay. So with these indeterminate systems, if you use the method of integration, you have an opportunity to do quite a bit of math. All right. For a question on the homework, okay, come on, whoops. Okay, we have this indeterminate system. Okay, and the question is, what is the displacement of the middle of the beam? Well, the slides online will give you a little bit of information, okay, in terms of how you do this, because I think these are a little bit tricky sometimes. Okay, but once again, we got to figure out, do the external equilibrium, right, and then figure out, even though you have unknowns, what the constitutive relationships are going to give us, then use the appropriate boundary conditions and plug them in, okay, to be able to solve. Okay. Now, what about using superposition for indeterminate systems, right? So that's the method of integration, right, which just to do a lot of math, essentially. And, you know, there's physics there, too. Can we use our tables to help us, right, to satisfy boundary conditions? Well, yeah, remember, even in exam 2, we had this problem where we said, hey, there's no wall, and now I put a wall there, okay? And once I put the wall there, what's going to happen? Well, I can figure out what the reaction force is necessary to get the displacement from now using that wall on that end to be equal to the displacement it had when the wall wasn't there. So yeah, we can play some tricks, and this uses our kind of creativity for figuring out, okay, hey, there's a displacement when there's no, right? Because remember, we want to get, essentially what you want to do is we want to break the problem into a set of determinant. You know, take this indeterminate system, we want to break it up into a set of determinant problems that we can add to each other. So if I've taken away this constraint here, what do we need to do to kind of mimic what's happening in this problem? Okay, so I've got, all right, I mean, and let's say we're, you know, what are we, you know, let's say that we're kind of interested in figuring out the displacement in the middle. Okay, that's what we're interested in. Okay, but even before I get to figuring out the displacement at any location here, how can I represent, what am I going to add to this to kind of make it the same? essentially I need equivalency, right? I need something here to be equivalent to this. This obviously is, so I've removed that. What is this applying? Or what was this roller applying? Jane?
Where you just add another displacement going the other direction.
Okay, so yes, if I'm thinking about displacements, right, I'm going to have a displacement going the opposite direction, right? What is this literally applying, though? It's a force, right? Okay, so I can think of that roller on the right as applying a force. And that force, right, is going, that force P here, right, that's going to go the opposite direction of this delta 1. And so what is my geometric compatibility here? Well, essentially it's that this delta 1 and this delta 2 are equal to each other. Or delta 1 minus delta 2 is equal to 0. Right? So this is where we have compatibility. And if I can satisfy that, then I will be able to figure out what the force P is on the right. Okay, so how do we do that? Well, these two equations, or these two determinate systems, have tables for them. Right? We have a table that describes the displacement at the end of a cantilever beam with a distributed load applied across it, and we have displacement at the end of a cantilever beam when there's just a concentrated force applied at the end. Right? So here's an equation for this one, and here's an equation for this one. And we set these equal to each other. Guess what? W naught is a known. Let's say that E is a known, I is a known, right? L is a known. What is not known? P is not known. Okay, so we can put them equal to each other, and then we can solve for P. All right. So now, in the context of what we've done in the past, or the last, right, we did the integral method previously to figure out what the external forces are. And you're like, this is crazy. This is just to figure out the external forces. Right? But that's the nature of an indeterminate system. We have this unknown, right? And the unknown is one of the external forces or one of the external loads. It could be a moment, whatever it is. Okay? So now that I've got P, let's say I want to know the displacement at the middle. If I want to know the displacement at the middle, well, how do we take care of this? We can use the tables again, all right? But first we write, okay, the displacement of this middle is going to be equal to this displacement, all right? And we're saying that's negatived, all right? Or however you want to, this is again a situation where you're like, okay, what is the direction? I mean, if I'm using a convention, oh, okay, that's good. We're getting close to the end. So if we're using a convention where this was positive or whatever it is, all right, or this is positive, these are going to have opposite signs, okay? So just make sure that when you plug in the numbers or you use the equations, right, that these have opposite signs. Okay. And from the table, we can use this one for displacement of M1, and we can use this for the displacement of M2. Okay. And then x at L over 2 is what we plug in here. All right, and that's what the value would be. Okay, and so you can calculate that out. Any questions on this? This requires a little bit of creativity. Okay, this requires a little bit of creativity and a little bit of sometimes thinking outside the box. And sometimes when I do it, I think out of the box incorrectly. Okay, and so in the real world, hopefully you're like, oh, I can find a table, or I can check with someone else, or you can do finite element. Okay, there's going to be question number 3, and this will be the last question that you have. All right, and again, since I think these are pretty complicated. This is essentially a huge hint in terms of how you can handle this problem. This problem is one where you can free this right end, okay, and then you just have this. And this constraint, okay, is essentially as if you have a moment, okay, and you have a force, okay, being applied to it. All right, so you can take a look at that. So here you go. We have a force on the right end. Okay, you have a moment on the right end as well. Okay, and this is how you can approach it. Okay, so the last topic is just beams as springs, and this is very short. That was the last problem that you have to do for the class, though. The bars as springs, we've talked about this before. We have equivalent spring constants, and we have related them to the material properties, and we can know that the spring constant is EA over L. We've also talked in the past about how extending the length of a bar is like adding a factor decrease to the spring constant of the bar. So you double its length, and you are going to be able to half its spring constant, or if you half the length, you're going to double the spring constant. Okay, which is kind of what we're talking about here. Okay. And we talked about this previously, and we know Hooke's law very well at this point in the context of statics. So, and we have this equation, So how do we handle cantilever beams? All right. And essentially, the answer is the same. We think about F equals or P equals K delta, right? And we have situations right now where we have a delta, which is the V, the lowercase v, and we have a force, right? So if P is equal to K times V, then K is just equal to 3I, or it's just equal to this factor that's multiplied by P flipped, right? And so now you can go around and take a look at these tables, and for these simple cases, or not so simple cases, if you're interested in saying, okay, how stiff is this when I apply this force to it, then here you go. Or how much rotation, for example, do I have at the end if I apply moment at the end, right? Then I would have like a KT analogy, or a KM if you want. Okay? You could have a torsional spring constant, is what I'm saying. And that's pretty much all you have to say. All I have to say about this. Right? So it's powerful in thinking about the design of mechanical components to be able to come up with a lumped parameter that is a spring constant for your system. Here's an example. We have this configuration where you have a force in the middle. Here's the table. Okay, lots of warnings. Okay, but we can figure out what the displacement is at the middle. That's going to be our delta. Our P is also applied at the middle. So pretty straightforward that the spring constant is going to be equal to P over delta, and that's what the spring constant is. And you notice a few things, right? Just like the K is equal to EA over L for the bars, right? You can think about it, okay, if I increase the stiffness, or if I increase the elasticity, the elastic modulus, right, that's going to make the K larger. If I increase the cross-sectional area, that's going to make the K larger. So now, here, I mean, we already talked a little bit about, okay, how much is a beam, how do the properties of the beam affect how much the beam can support, right? And we talked about that. You know, it's going to go with the thickness cubed. It's going to go with the width. It's going to go inversely with the length, right? These parameters we talked about in, I think, the very first day of class. So this is not talking about how much it can support, but this is talking about how much it will deflect. Okay? And so we can see once again, stiffness is going to be proportional to elastic modulus. We can see it's not the cross-sectional area of the beam, but it's the second moment of area of the beam that's going to limit the moment, or then limit the deflection. Okay. And if you make it longer, it goes with a factor of 3, and the deflection does. Okay, or with the cube, a factor cubed of that. So this is it. This is the end of the class. All right. And today we talked some about superposition, talked about indeterminacy, and we talked some about beams as springs. Okay. And if you'll forgive me, okay, I like to do 2 things though. One, I just like to talk about with you what you think we've learned in this class. Okay, what have we learned? Okay. So I think a big thing that we've learned, right, is that we've now been able to take either material testing or loads on structures and understand that these result in stresses. Right? This is a huge deal, right? Before you walked into this class, you're like, okay, I know what an internal shear force is, I know what an internal force is, I know what an internal moment is, but why are they important? Okay? So this is a big fundamental step in our understanding, because once we know these shear and axial or normal stresses, then we can figure out and ask ourselves the questions: will it break or will it fail? Okay? And now you can walk around the world and look at any object essentially that's under a load. So unless it's in microgravity, okay, it's going to be under a load on Earth, and you can have some idea of why it's in static equilibrium and not breaking. Okay, and if you were to substitute materials, right, you've got an idea of, okay, what the behavior is going to be.